geometric sequences. So when we're talking about graphing and classifying, this is what we are graphing and classifying: sequences. Now you might be thinking, okay, what is that? Well, it's nothing more than an ordered list of numbers. Okay, and they have to be ordered because we're going to be finding patterns in them. And we're going to classify them based on those patterns. Okay, so the first type we're going to talk about is geometric. Okay, a geometric sequence has a common ratio. Now, that should be ringing all kinds of bells because we've been talking about common ratios for the last couple of days. Which one of our function friends has common ratios? Ooh. No.
Am I right?
No. The one with the multiplying pattern? Yes, exponential. Okay, so the other thing that has a common ratio is the exponential function family. Okay, so if I look at this ordered list of numbers, this sequence, and I try to see what's happening every time, what pattern do you see? Be very careful. Is it adding or is it something else? Multiplying by what? By 2. Okay, so whatever we're multiplying by is defined as our common ratio, and we call that R. So this R is 2. R is for ratio. So I'm going to say that again. R is what we multiply, not what we divide by. That's going to be very important for us when we write these rules. Okay, next we have arithmetic sequences. Yeah, you might think that I don't know how to speak, and it is the same spelling as arithmetic. Arithmetic is a noun. It's like adding and subtracting and doing figures, right? Okay, arithmetic is an adjective. It modifies the noun sequences. So arithmetic sequences, it's pronounced differently. So the stress is on a different syllable.
I did not like when you said syllable.
I know, it was a joke, right? Because I changed this. It was a joke. I'm hilarious. No? Syllable? Syllable? Arithmetic? Arithmetic? All right, tough crowd. All right. Well, you get what you pay for, kids. You get what you pay for.
We didn't pay for anything.
Right, so you get
Nothing.
garbage. You get garbage. All right, I'm just kidding. All right, so arithmetic sequences have a common difference. Okay, now that should be ringing bells.
What class then?
Okay, yeah, so subtracting, okay, which one of our friends has a common difference? We know it's not exponential because that was a common ratio. The linear. Okay, so common difference, the linear has it. Okay, quadratic, remember we had the second difference, the constant second difference. Okay, so what is our common difference in this sequence? What are we adding every time? Hey, yeah, we're adding 0.5. You thought you'd never get to use a decimal in this class, and here we are using a decimal. Okay, today was the day. All right, so our D, common difference, right, that kind of makes sense, was 0.5. 0.5. Okay, questions about that? Okay, so if we have a multiplying pattern, we're going to say it's geometric. If we have an adding pattern, we're going to say it's arithmetic. Okay, the math gods smiled on us when they made adding and arithmetic both start with A. Okay, that's how you're going to keep them straight. Thank you, math gods, for your mercy. All right, here we go. So on this table, we are going to find the pattern so we can classify it. We're going to say if it has a common difference or ratio, and we're going to say what the D or R is. So looking at this set, this sequence, what do you see? What's happening every time? Adding 4. So if it's adding, it's
Common difference.
okay, a common difference. And what's the difference?
D equals 4.
D equals 4. So what sequence type is it?
Arithmetic.
Yeah, arithmetic. Okay. Next one.
-5.
Okay, -5. You can think of it as adding a -5, right? Okay, so if we're adding, it's arithmetic. Okay, it has a common difference. And that common difference is -5. We can't just say 5 because we're not adding 5, we're adding -5. All right, you guys are going to be great at this, I can tell. All right, next one.
Times 3.
Okay, every time we are multiplying by 3. So what type is this?
Geometric.
Yes, geometric. Okay, so instead of a common difference, we've got a common ratio. And so we know that R has to be 3 because that's what we multiplied by. Okay, this next one is a little tricky.
We're dividing by 12.
Close,
6.
closer,
3. Still 3.
closer. Yeah, we're dividing by 2. Okay, so if we are dividing by 2, remember that we have to change it into multiplying. So if we're dividing by 2, it's multiplying by 1/2. Because I can't say that the common ratio is 2 because that would mean I was multiplying by 2, but I'm not. I'm multiplying by 1/2, right? So this is still geometric. Okay, it has a common ratio, and that ratio is 1/2. Okay, hopefully that was pretty easy. Okay. You guys are gonna like this next bit too. It doesn't really get worse today, it just stays nice. This is the most rarest of days. All right, so we have this cute little table that has a sequence in it. Okay, you can see it's going 15, 12, 9, and 6, right? So on the right side of the table, these are the terms of the sequence. Okay, on the left side of the table, these are the term numbers. Okay, so term number 1, the first term is 15. Term number 2, the second term is 12. Okay, do you see how this has this little crazy A with the subscript? Okay, I'm going to show you how to use that real quick. It's going to look weird, but just bear with me. Okay, so if my N is 1, then my term 1, my A sub 1 is 15. If my N is 2, my term 2 is 12. Do you see what's happening? It's just a way to give the term a name. Okay, so I can say I want the 6th term. Well, that would be A sub 6. Why? Because not so much in this class, but in future classes, we'll do a lot of solving and stuff for particular terms. And we'll want to go out way into the future where you don't want to just make a list and find it the long way. There's a short way. So if n is 4, our a sub 4 is 6. Okay, so that's the table. Let's look for a pattern in our terms. Yeah, from 15 to 12 to 9 to 6, we're subtracting 3 every time. So that is our common difference, D. Our D is negative 3. So if we have a common difference, what type is this? Arithmetic. Okay. All right, let's graph this guy. Now, we talked about how this was a table. Doesn't this look like an input-output table? Which side of the table are x's usually on? Yeah, over on the left. So this is a big hint to us how to set up our graph. We're going to treat the n's like the x's and put them on the x-axis. And we'll put the a sub n's on the y-axis. So n's will go here, and a sub n's will go here. So term number is the independent variable, and the term is the dependent variable. Doesn't the term of the sequence depend on how far along in the sequence it is? Yeah. All right, so let's do first term, second term, third term, fourth term across the bottom. Now we have a problem because we have to get all the way up to 15, but I only gave you 10 boxes. Yeah. Okay, so both 5s and 3s, even 2s, they would all get us to past 15, right? But if you look at our terms, do you see how they're all divisible by 3? So 3 is the best choice for skip counting and labeling our axes. Does everybody understand why? It's going to give us pretty points. Okay, so we're going to skip count by 3. So 3, 6, 9, 12, 15, 18, 21, 24, 27, 30. Okay, my first term is 15. Second term is 12. Third is 9. Fourth is 6. Now, before you connect them, don't connect them. Okay, write yourself a little note. Don't connect. I know it's really tempting because pretty much everything we've graphed in this unit so far, we've connected. Think about all of the functions that you have graphed so far. What has their domain been, pretty much? All real numbers. So they go forever and ever, right? They don't stop. And are there any breaks in the graph? No. So we were able to say it was all real numbers and connect those points because they were continuous, okay? We had all of the little weird in-betweeny points between the points that we plotted. Do we have, for example, a term 1 3/4? So we can't put a dot there, right? Do we have a term 2.5? No, we just have our first term, second term, third term, fourth term. So we can't connect them because we don't have the in-betweenies.
So we have to list them out.
So they're already listed for us, but you're thinking kind of along the right lines. So these are just discrete points. They're only at those locations. They're not continuous representations of what the whole rest of the function looks like, okay? All right, so we don't have the in-betweenies, so we do not connect for sequences. But we can use our imaginations. Does everybody see that if we did connect, they would fall on a straight line?
Mm-hmm.
Okay, so that's where we get our connection to the linear function. So you can just connect them with your brain, but not with your pencil. Okay. Oh, really quick. You guys don't have to flip back. I just need to remind you. This is something that is pretty easy for kids. They do a great job of it, so we don't have to practice a lot. So on the test, when we do this, it's really easy to forget labels, okay? And then I have to take off points for something that you totally knew, right? You just didn't write it down. So don't make me be that guy because I hate that guy. So don't forget your labels. Okay, it's like a point. So what happens is that kids will connect the points and they'll forget the labels, and then they're losing a point or two per graph. And then I'm like having to take all these points off and I feel like a jerk. So don't do that to us. All right, let's look at this number 6. Okay, so here again we have our term number. Whoops, not term. Okay, and then these are our actual terms. What is happening? Multiplying by 1/2 again, good. Okay, that is our R, our common ratio. So if we have a common ratio, what's our sequence type? Geometric, good. Okay, and we can compare geometric to what kind of function? We'll come back to that. Let's label ends across the x-axis, 1, 2, third term, fourth term, and our g sub ends on the y-axis. Okay, we got to get to 16, but I only gave you 10 boxes. What are we going to do? Count by twos. I like it. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, my first term is 16. Second term is 8. Third term is 4. Fourth term is 2. Do I get to connect my points?
No.
No, I do not. Good. I don't have any of the in-betweenies, and it doesn't go on forever. I just have those 4 terms. So, what kind of curve do they fall on, though, those points? Yeah, exponential. Looks like a ski slope. Okay, I want to show you one more thing. Don't erase because you'll get mad at me because you don't actually have to change anything. So one of the other things I see kids do that you're not supposed to do is they'll put a 1 here and then they'll start skipping. You see that this is problematic because I changed the size of my jump? You can't do that. You either have to skip 2 every time like we did, or if you want to do your graph like 1, 2, 3, 4, you can do that. It'll just be squished horizontally, okay? But don't change the size of your jumps.
What do you mean?
Okay, so I don't do this. Do you see how this is a jump of 1 and then this is,
Oh,
they're mismatched? Don't do that. Okay, one thing I forgot to tell the other classes that I'm going to tell you guys, and this is the only thing we're going to do on the next example. Do you see that for this one, I have to get all the way to 27? Okay, so we're going to count by 3s. Okay, I'm going to show you what not to do. Don't do 3, wait. Don't do 1, 3, 9, 27. Do you see that you can't do that? Okay. That is a different kind of scale. That is what we call a logarithmic scale, and that is not what we're looking for here. If you do that, these exponential shaped points are going to look like they're in a straight line, and you're going to be very confused. Okay, so don't give me a logarithmic scale. Give me a regular scale. Okay? Right. Okay. So really quick, if we do that and we say 3, 6, 9, 12, do you see that my first point isn't going to be at 3? It's going to be like 1, 1 is going to be here. It's okay if it's not on a grid line. Okay? That's all I have to say about that one. Don't do logarithmic. I'm going to put that back on here and cross it out. 3, 9. Oh, no, it was 1, 3, 9, 27. Okay, don't do that. Okay, do you guys agree that we don't need to do that one?
Mm-hmm.
Okay, perfect. Let's talk about these. All right, my Tuesday, Thursday people already know how to do these, so you're going to help the rest of us out. We have to decide whether each of these is going to be linear, quadratic, exponential, or none. Okay, so my linear, I'm looking for a straight line. Okay, I'm looking for a function where x and y are on opposite sides, and my power of x is 1. Okay, for quadratic, I'm looking for a U shape, either up like a cup or down like a frown, and I'm looking for a function where the highest power is 2. Okay, what kind of shape graph am I looking for exponential?
Where the x is the exponent.
Okay, I'm looking for something where we've got a base raised to an x power, and then the graphs kind of look like ski slopes. Okay, graph looks like a ski slope. Okay, that's what we're looking for. So this first one is a little tricky because I just told you we're looking for x's that have a power of 1, right? But you know from unit 2 that if we distribute that 7x, we will get y equals 7, add the powers, x squared minus 21x. So it looks at first glance like it's linear, but what is it really? Quadratic. Okay, if you're like, I'm not going to remember that, I'm going to show you how to get a picture. So go to your calculator. Go to the y equals button, top left.
Oh, wow.
And it gives you all of these y's where you can put in a rule. So I already have my rule put in. Would you guys put yours in, please? The X button is right here next to the alpha button. Clear that out. 7x, open parentheses, x minus 3 close parentheses. Good, have my graph.
Wow. Can you tell me I've been doing this for years and you've gotten to it?
Okay, did everybody get a parabola? Or at least you can only see part of it, right?
Yeah.
Yeah. You can see enough of it to know that it goes down and comes back up. So that's definitely quadratic. Let's try the next one. If we look at the power of x, what do we expect it to be?
Linear.
Linear, but let's check it. So I'm going to go to y equals, clear that out. 7x, is it minus 5? Okay, graph it. Boom. It's a line. It's a line. It's a line. It is definitely linear.
How do you type a y on the calculator?
Oh, that's a good question.
You have to do alpha y.
No, do you see that it already has on the y equals, it already gives you the y?
Oh.
But the y is alone on its side, right? It's all alone on the left side. Is this y all alone?
No, it has x.
Right, so we have to get rid of the x. What operation is happening between the x and the y? Okay, it's multiplying, so we have to divide them apart. So divide both sides by x, and this is what you put in. You already have the y equals, put in 2 divided by x. It kind of looks like it might be exponential, but it's not. Whenever we do exponential, do you see that we only get one ski slope at a time? Right? Okay, this one you get 2. There's one over here and one over here. So this one's is actually none. Okay? You're not allowed to get 2 ski slopes at a time for exponential. You only get 1. All right, what do you notice about y equals 8 over x? It's just like the last one. It just has a different scale factor. Okay, so if you think about it, if I were to rewrite this x, do you see how the x is in the denominator? And if I wanted to write it in the numerator, I would have to give it a negative power. So I can rewrite this as y equals 8x to the negative 1 power. Everybody okay with that? Negative power rule? Do you see why it's not exponential? For exponential, I want my x to be the power, but here is my x the power. This is something else. This is called a rational function. Okay, you won't do those until algebra 2. So this is none.
Do you teach algebra 2?
No. But I have vague recollections of what they do. I remember little bits. All right, what about f of x?
It's exponential.
It's exponential. Look, it looks just like that, where 5 is the b. Okay, so this is exponential. Should give you a ski slope. All right, what about this f of x? This one's tricky like the first one. I'm trying to get you to say quadratic, but don't fall for it, because when we distribute the x squared, we will get f of x equals 2x cubed, right? Because we add the 2 and the 1 powers, minus 3x squared. So if it's cubed, it is cubic, not quadratic. And if you put that guy in the calculator, you will get a crazy function that looks like this. Try it out. Here, we'll all do it together. Okay, what was it?
2x cubed
Oh,
minus 3x squared.
I was going to put the original one in. X squared, open parentheses, 2x minus 3. Is that right?
Mm-hmm.
Okay, then I go to my graph. There. Isn't that fun? You guys ever seen a crazy function like that before?
No.
Okay, I have a thinker for you. Okay, look at this linear. How many directions does a linear go in?
1.
How many directions does a quadratic go in?
2.
How many directions, boom, 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 does a cubic go in?
1.
1, 2, 3, because it goes up, down, up, right? How many directions do you think a quartic will go in?
4.
Yes, it's a pattern.
Oh my goodness.
Aren't patterns fun?
Not really.
No? Oh, okay. All right. This one is kind of goofy because I've got x's with my y's. I want my y alone so I can test it in the calculator. How do I get rid of adding a positive 3x? subtract. So I subtract 3x from both sides. These cancel. Okay, I'm left with y equals, can I combine my 12 and my negative 3x? You are correct, I cannot. They are not like terms. But now I can put them in the calculator, and the calculator can handle it. What did you get? Linear. You get a straight line. Notice that the power on the x stayed 1, even when I added or subtracted it to the other side. All right, the next one's kind of easy. Look at where the x is. Yeah, it is. The x is the power, so this one's exponential. Okay, it's ski slope. All right, the last one is one of my favorite tricks. It is quadratic because when I distribute, I get x squared plus x minus 8x minus 2. And you can see that my highest power is 2, so I better pick quadratic or I'll be in deep doo-doo. And if you put it in your calculator, you get a parabola. Parabola. Okay, that's it. That's the end. You made it. Okay, we've got lots of work time.